Hello and welcome. The purpose of this video is to review the idea of stereoisomers. So let's start here with the idea of isomers in general. What is an isomer? Well, an isomer or a set of isomers are two different molecules with the same molecular formula. So you could imagine something like an ether and an alcohol. You could also imagine something like but1-ene and but2-ene. These are the isomers that we had already talked about, and these are structural isomers, where they have the same molecular formula, but different condensed formulas. They even have different IUPAC names. The bonds are in different places. Now, the new type of isomer that we've seen is called a stereoisomer. With a stereoisomer, the bonds are in the same place. Except for whatever prefix we need to add, they'll have the same IUPAC name. And one of our jobs with stereoisomers is learning whatever prefix we actually need to add. But other than that, they'll have the same name. The bonds are in the same place. So the thing that's really different is the 3D placement of the atoms. We learned about several different types of stereoisomers. One are conformational isomers, and the others are all configurational isomers. Conformational isomers, these come from rotation around sigma bonds, and specifically those carbon-to-carbon bonds. That's where we saw the Newman projection. Those are always happening. It's just how the hydrogens are lining up around the two carbons that are rotating. Configurational isomers, these ones come from the bonds actually would need to break in order to form the other isomer. So the options we have here are cis-trans, EZ. Both of these deal with alkenes or C double bond C. Cis-trans can also refer to a cyclical molecule, and optical isomerism. All right, so let's review cis-trans EZ and then the optical isomerism, and that's the enantiomer and diastereomer. All right, so let's take a look at but2-ene, and but2-ene could look something like this, or it could look something like this. So the methyl groups could be across the double bond or on the same side as the double bond. The reason that these are not conformational isomers is that there's no free rotation around the double bond. So if two of the same substituent, we're looking for the same substituent, if two of the same substituent are on opposite sides of the double bond, that's called the trans isomer. If they're on the same side of the double bond, that is the cis isomer. All right, so sometimes that cis and trans is just not going to be specific enough. So I want you to consider the molecule that I've drawn here. 1-bromochloro, 2-methyl-but1-ene. So I have my chlorine and my methyl group on the same side, or I could have my bromine and my methyl group on the same side. So I can tell that I have two isomers here, that they're not the same molecule because different things are on different sides of the double bond. However, cis and trans does not work because I don't have two of the same substituents on each of the carbons in the double bond. I have a chlorine and a bromine, a methyl and an ethyl, which of course it's not really an ethyl, it's actually just attached to the full carbon chain, but I don't have a situation where I have CH3, CH3, the same thing. Or I know we don't show it, hydrogen and hydrogen, the same substituent. So in this case, cis and trans is not going to work. I need something that's more specific. And so I'm going to use the EZ system. And EZ should always work with any isomers that have a double bond, including those that we can name with cis and trans. It's just that EZ always works, cis and trans only sometimes works. So cis trans isomers for double bond isomers are one subset of the isomers that exist, and then EZ isomers are more specific, and they can name any isomers that exist across a double bond, including those ones that could be named by cis trans. All right. So with EZ isomers, we use what's called the CYP priority rules, which is just higher atomic number gives me a higher priority. So pretty straightforward, chlorine versus bromine. Bromine has a higher atomic number, so it has a higher priority. So I look at one of my carbons, I check the two substituents, bromine has a higher priority. Now I look at the other carbon, and I see that the second carbon is attached to a carbon and a carbon. That's interesting. Those have exactly the same priority. Well, that means I need to keep going down the line. So this carbon is attached to a hydrogen. This carbon is attached to, well, hydrogen, hydrogen, but is also attached to another carbon. And so because it's attached to another carbon, I'm now comparing what the first carbon was attached to, what the second carbon was attached to, and of course carbon has a higher priority than hydrogen because higher atomic number, and so that makes this group of two carbons higher priority than the group of one carbons. So bromine and then the two carbon chain have higher priority. If the higher priority groups are on the same side, that is the Z isomer. I remember that because same kind of sounds like if I replace that S with a Z, call it ZAME. Same, ZAME, Z for the same side. Here, my higher priority groups are on opposite sides, and so I would call this E. All right. The last type of isomers we looked at is optical isomers. Optical isomers happen when you have a chiral carbon. A chiral carbon is when we have different atoms or groups attached to a carbon. So that can be something pretty straightforward. I could have bromine and chlorine and fluorine and hydrogen attached to a single carbon. That would make the carbon chiral. It could also be referring to different groups. So if I had something like this, okay, let's do bromine here and CH3 and hydrogen. Okay, so I want to take a look at this carbon specifically. This carbon, well, it's attached to a hydrogen and a bromine. So those are two different things. And then it's attached to a carbon and a carbon, but let's see if those two carbons are the same. Well, it turns out they're not. This carbon is just a methyl group, it's CH3. The other carbon that we're attached to is attached to not just hydrogens, but a second carbon. So I see that the carbon in green is actually attached to two different groups. So we're not looking at just the atom we're attached to, we're looking at everything the carbon is attached to. It kind of reminds me of when we were picking out hydrogen environments for NMR, and we look at everything the hydrogen's attached to see if they're equivalent environments. So we're trying to figure out if these two groups are the same thing, and they're actually different because on one side the carbon is attached to C2, H, 1, 2, 3, 4, 5, and then on the other side the carbon is attached to CH3. Then it's attached to a bromine and a hydrogen, so it actually makes the carbon in green here chiral. All of the other carbons are attached to two hydrogens, so those are exactly the same, so that would be the one chiral carbon in that molecule. You can do the same thing if you have a cyclical molecule, for example. And so if I have something like this, and let's say there's a bromine here, all right, well, if I look at this carbon, it's attached to a bromine, a hydrogen, and let's actually put a methyl group here. Okay, so this carbon that I've outlined is attached to a bromine, a hydrogen, and then it's attached to a carbon and a carbon. But I see that on either side, my carbons are not equal because one of them has a methyl group coming off and the other does not. So that would also make this carbon chiral. So we're looking for carbons attached to 4 different atoms or groups of atoms. So you need to look at the entire molecule to figure out if you have a chiral carbon. All right, so if I know that I have a chiral carbon, if I have a molecule with a chiral carbon, then I can have optical isomers. We're going to pause for a moment so that I can show you what this actually looks like with the model kits. Hi. All right, so let's take a look at some chiral molecules. I have here a molecule that has 4 different substituents, and I'm just using these 4 colors to represent 4 different things. It doesn't really matter what they are, but I know it's chiral because this one carbon is attached to 4 different things. So we're going to take a look at what kind of isomers this can have. Whenever I have a chiral carbon, I know that I can have optical isomers. I can have enantiomers. So let's take a look at a second molecule. And here I'm going to line this up so that we can see. All right, so here I have a second molecule, and I see that every substituent can line up with each other. What that's telling me is these two are actually 2 of the same exact molecule. So these are not isomers. This is just a repeat of this one. These are the same molecules. However, if I switch this, if I switch one of these bonds, let's see what happens. I'm going to line up my my orange, line up my white, but now look what happens. My blue and my purple are lined up, my blue and my purple are lined up. So these are actually no longer superimposable. They're no longer exactly the same because I can't line them up perfectly with each other. I no longer have 2 of the same molecule. So when I have a chiral carbon that has a different arrangement of the substituents, this is going to be an enantiomer. How do I check that it's an enantiomer? Well, I can see these make a mirror image of each other. So if I had this arranged like this and I put a mirror here, what I would see reflected back at me is this. I see that now my blues are lined up, my whites are lined up, my purples are lined up, and my oranges are both going back. So these just made a mirror image. These are called enantiomers. If I only have one chiral center, the only type of optical isomer that I could get would be an enantiomer. And I can check that they're enantiomers because they're mirror images of each other. These are also called optical isomers because they're optically active. They rotate the plane of plane polarized light. All right, I could have another situation where I have more than one chiral center. So let me build that. And we're going to build it like this and then add our second. Carbon. And I know this is riveting content, watching me use the model kits. Okay, here we go. So now I have two chiral centers. I can see that both of my carbons here are connected to 4 different things. All right, so both carbons connected to 4 different things. So 2 chiral carbons. So now it's going to be a little bit more complicated to figure out what kind of situation I have. So here I have exactly the same molecule. I have 2 of the same molecules. Every single atom is lining up, superimposable, so this is not an isomer. This is just 2 of the same molecule. I could have a situation here where I make an enantiomer. So let's see what that would look like. I can switch out my atoms here. Let's flip these. All right. And now if I line up my molecules, I have an enantiomer. Why is this an enantiomer? Well, because they've made a perfect mirror image. I'm no longer superimposable. I see that green, yellow, yellow, green. I don't line up, but I do line up back here. So no longer superimposable, but they do make a mirror image. So this is called an enantiomer, just like before. However, when I have 2 chiral centers, there's other things that might be going on. I could also have what's called a diastereomer. So what would that look like? Well, that would look something like this. All right, so I'm just flipping 2 of these atoms. All right, so down at this bottom carbon, I still have the mirror image business going on, but up here at the top carbon, it's no longer a mirror image. This top carbon is actually superimposable. So the entire molecule is not a mirror image because up at the top, it's not making a mirror image, but it's also not 2 of the same molecule because this carbon with orange and purple and blue is not superimposable. So this would be a diastereomer. If I have more than 2 chiral centers, I need to figure out, is the entire molecule a mirror image, making it an enantiomer, or is only part of the molecule making a mirror image? And let me show that really well. So the bottom is still making a mirror image, whereas the top does not make a mirror image. The bottom does. The bottom lines up like a mirror. The top does not, as you can see. And so that makes it a diastereomer because I don't have a full mirror image up and down the molecule. All right, I hope that helps. All right, so some other important things to know about optical isomerism is, in order to figure out the number of enantiomers or the number of optical isomers that's possible for a given molecule, we use this formula. Whoops, that looks kind of crazy. We use this formula 2 to the power of n, with n being the number of chiral carbons. So if you have just one chiral carbon, 2 to the power of n equals 2 to the power of 1 equals 2 enantiomers. That would be kind of the most basic case. If you had 2 chiral carbons, well, you would actually have 4 possible enantiomers. So to figure out the number of optical isomers, you can use this formula 2 to the power of n. Other important things to know. Enantiomers have the same physical properties except for the rotation of plane polarized light. They have the same chemical properties except for when they're interacting with other enantiomers, like in the human body. Interacting with other enantiomers. And in the human body, we saw that with the drug thalidomide, which was interacting in the human body to cause both a reduction in morning sickness, but also, unfortunately, an increase in birth defects. And so we saw similar chemical properties, except when it was interacting with other enantiomers in the human body. The other thing to know is if you have a mixture of 50% and 50% of two enantiomers, that's called a racemic mixture, and it all of a sudden shows up as being optically inactive because each enantiomer is rotating the plane of plane polarized light, but in the opposite direction, so they cancel each other out. The important thing to know about diastereomers, they can have different physical and chemical properties. They can line up differently, so they can get different IMF, they can get different interactions, do different reactions, and they're only sometimes optically active. We don't need to predict when, but they're not always going to be optically active. The other thing is you need at least 2 chiral centers. So if I have more than 1 chiral center, I need to figure out, do I have a diastereomer or do I have an enantiomer? If there's only 1 chiral center, I need to figure out, do I have the same molecule or do I have an enantiomer? So let me just summarize what I said, and then we'll be done with stereoisomers. So if I have only 1 chiral center, the question I'm asking myself is it the same molecule, 2 of the same molecule? So that would happen if they were superimposable. Or is it 2 different molecules, which would make them enantiomers? If I have 2 or more chiral centers, I need to figure out, do I have the same molecule? Do I have 2 different molecules? And if I have 2 different molecules, are they mirror images, making them enantiomers? Or are they mirror images at only some of the carbons, so not fully mirror images, making them diastereomers? All right, I hope this helped. Thanks for watching.